Welcome to Basics of Finite Element Analysis course. This is a MOOC course, part 2, and today this is the second day of the first week of this course. And what we will do today and also pretty much throughout this entire week is a quick review of whatever we discussed in detail in part 1 of this course, which was Basics of Finite Element Analysis, part 1. So, the first thing we are going to review is get a feel of what is the fundamental principle which underlies finite element analysis. And we will start with an analogy, and then we will actually develop the finite element equations and solve it. So, the analogy is that suppose I have so this is x axis and this is y, and suppose I have a curve, and let us say this curve is y equals x cube. Okay. And let us say I am interested in finding this area under the curve for the region x is equal to 1 to x is equal to 5. So, this is the area which I am interested in finding out. Now, one way to find this area is, because I know this function very nicely, so I can integrate this equation, because integral of this function represents the area under this curve, where is, so area equals integral of y times dx, that is, and in the limits 1 to 5. So, I am going to integrate this x cube dx, and that equals x4 by 4 evaluated between the limits 1 to 5. So, that is equal to 5 to the power of 4 minus 1 divided by 4, and this value turns out to be 156. Okay. So, this is one approach, but if this curve was very complicated and if we cannot calculate the exact integral of this function, then this approach will not be efficient. So, the other approach is that I break this area into small pieces. So, let us say here x is equal to 2, 3, 4, and I am going to break this area into small pieces. Okay. So, what I have done is, my domain is, that is the range of x is from x is equal to 1 to x is equal to 4, and I have broken my domain into 4 elements. First element is x equals 1 to 2, second element is 2 to 3, third element is 3 to 4, and fourth element is 4 to 5. And so, now I have 4 areas, and I will call them area A, B, C, D. So, total area is equal to A plus B plus C plus D, and this, if we do our math correctly, it should be close to the actual area, which is 156. So, now we are actually going to compute the values of these areas in several ways. So, but before we do that, let us calculate the value of y. So, here when x is equal to 1, y equals 1, because x cube of 1 is 1. When x is equal to 2, then y equals 8, when x equals 3, then y equals 27 when x equals 64, and when x equals 5, then y equals here 125. 5 cube is 125. And what we will also do here is also evaluate the values of middle points. So the first middle point is 1.5 cube, so that is 3.875. The second middle point is 2.5 cube, so this is 15.625. The third middle point is 3.5 cube of 3.5, so that is 42.875, and the fourth middle point is 4.5 cube, which is 91.125, and we will see why we need these midpoints. Okay. Now what we do is we start calculating the values of area A, B, C and D, and we do it in 2 or 3 different ways. So in the first case, case 1, I assume that this area, so this is area A, is approximately equal to this area. Okay. So what am I assuming? That so this is point 1 and 2. So the variation of y between 1 and 2 is constant. I am assuming that value of y between points 1 and 2 is nothing but constant. This is I am assuming. In reality it is not true, but I am assuming that it is constant and its value is same as that which is at 1. So this height is 1 and this width is 1. So area A is equal to 1. Okay. Because this height is 1, cube of 1 is 1, right? Similarly, for area B, it is 2 cube into 1 is equal to 8, right? Similarly, area C is equal to 3 cube into 1 is equal to 27, and area D is equal to 4 cube into 1 is equal to 64. Okay. So here area A, B, C and D we have evaluated assuming that these areas are nothing but rectangles, right? Or in other words, the variation of y across each element is constant. It does not vary, so it is constant. So in such a case, total area is equal to 1 plus 8 plus 27 plus 64, and that equals 100. So my error is equal to 100 minus 156 by 156, because the actual area is 156. So this is equal to minus 36%. So if I break the whole domain in this case into 4 individual units and assume that y is constant across each element, then I have an error of 36%. Now I do another approximation, case 2. Okay. Here I assume that this area A is approximately equal to this kind of a trapezoid. And here the height of trapezoid on this side is 1 and the height of trapezoid on this side is 2 cube. Okay. So, in this case A is equal to 8 plus 1 by 2, right. 8 plus 1 by 2 times 1. Area B using similar method is 8 plus 27 by 2 into 1. Area C equals 27 plus 64 by 2 into 1, and area D is equal to 64 plus 125 by 2 into 1. Okay. So in the first case, I am assuming that the value of y is constant along each element. In the second case, I am assuming that value of y is linearly varying across each element. And in this second case, total area, if I add up all these values, I get it as 162, which means my error is equal to 162 minus 156 divided by 156, and that comes to be plus 3.9%. So what we immediately see is that because I changed the nature of function from constant to linear, my error significantly got reduced. Okay. So this function which we assume that it is constant in first case and it is linear, this is called an interpolation function. So what we are seeing is that the accuracy depends on our choice of the interpolation function very strongly. We will do one more case, case 3. And in this case, I assume, so this is, okay, here in reality y is equal to x cube, right. That is the actual function. But suppose we do not know this function, then we assume, in first case we had assumed that y was constant, second case we were assuming that y is a linear function. So we assume that it is not a linear function, but it is having some quadratic relationship, okay, y equals a plus bx plus cx square. So we are assuming that this curve or at the top edge is varying in a quadratic manner. We are assuming this. In reality it is cubic, but here we are assuming that it is quadratic because the mathematics becomes a little simple, that is all. So if we do this, then we can again calculate the values of different areas, but then in this case we have to find what are the values of a, b and c. Okay. So unless we know a, b and c, we cannot find out the area under this curve. Okay. So first we will see how to find out the area under this, the values of a, b and c. So at this point we know that the value is, this height is 1, this is area A, and this height is 8 or 2 cube. But to find A, B and C, we need a third condition, right. So we should also know the value of B, this height at one more point, and in this case we selected the midpoint, okay, and this height we said that it is 3.875. Okay. So this is 3.875. Okay. So now we find out the values of A, B and C by writing out three different equations. The first equation, so this is y1, this is y3, y2, this is y3. So we write y1, y2, y3. See, these are known. Okay. So y1 equals A times B times x1, right, plus C times x1 square. So I can write it as this. So this is my first equation, y1 equals 1 times A plus x1 times B plus x1 square times C, where x1 is equal to 1, x2 is equal to 1.5 and x3 is equal to 2. This is x1, this is x2 and this is x3. Okay. Similarly, y2 is equal to A times 1 time plus x2 times B plus x2 square times C. And similarly, y3 is equal to A plus B x3 plus C x3 square. Okay. So this y vector is known. This is also known and this is unknown, right. So these are three equations, three unknowns. So I can calculate A and B can be calculated. Okay. Once we know A, B and C, then area A is equal to what? Whatever A, B and C we calculated, we can calculate from x is equal to 1 to 2, A plus Bx plus Cx square dx. In this way we can calculate area A. Okay. By integrating A plus Bx plus Cx square in the limits x is equal to 1 to 2, we can find out area A. Understood? And if we do all this math, we find that this area comes to be 3.75. Similarly, we go to the next element. There again we assume that y is equal to A plus B plus Cx square, and we again recompute ABC because our y vector and this matrix has changed, right. So we have to again recompute ABC, and then once we recompute ABC, we again use this type of a relation to find the second area. So B is, we find that area B is equal to 16.25, area C is equal to 43.75 and area D equals 92.25. Okay. And if I add up all these areas, then total area I find that it is equal to 3.75 plus 16.25 plus 43.75 plus 92.25, and that comes out to be 156. Okay. So in this case it comes out to be the exact area which was computed earlier. So from this what we see something very significant, that the accuracy in this approach where we are breaking up the domain into smaller and smaller units, it depends on three things. First is, so accuracy depends on first thing is it depends on number of elements. So in this case we had developed 4 elements, right? If we had created 20 elements, then even with a constant y function, things would have been much more accurate. Second thing is accuracy depends on nature of interpolation functions. Nature of interpolation function. So in the first case, if so let's call this number of elements as n. So as n goes up, what happens? Accuracy also goes up. Nature of interpolation function, so this can be measured in terms of n, which is the order of the polynomial. So as n goes up, so does accuracy. Okay, this is what we saw just now. And the third thing is computational accuracy. And what does this mean? That suppose you are dividing 4 by 3. You can have several answers. One would be 1, another answer would be 1.3, another answer would be 1.33, another answer would be 1.333. So it depends on how many places of decimal you are evaluating each number. So the accuracy of the overall finite element solution also depends on this computational accuracy. So this can be measured as number of significant digits. Okay, as this number goes up, so does accuracy. So the accuracy in of finite element solutions, it depends on these three things: number of elements, nature of interpolation function, and computational accuracy. So this completes today's lecture. In the next lecture, we will actually start talking or reviewing the mechanics of finite element method, that what are the different steps, and then later as the week progresses we will actually do an example, so that whatever we have learnt in the last course we are able to capture in full in this course. So thanks a lot, and we will meet tomorrow. Bye.